So tomorrow we're starting the chemical reactions labs, 5, 6, 7, and 12. Some of the material you're going to need from chapters 9 and 19 and some of the latter chapters. So we'll just jump ahead a little bit and take a look at a couple of sections from that. But you'll need goggles. You can get new goggles, the visor goggles from the bookstore, or if you don't mind used goggles, you can use a used pair of goggles. We have a lot of used goggles there. You'll also need shoes, no sandals for tomorrow's lab. Other things that are nice to have are gloves, nitrile gloves, and lab coat.
Can I use hairdresser gloves?
Yeah.
Like this?
Yeah, you could use whatever gloves you want. That's fine. All right, we're supposed to be in chapter 7. I'm going to finish chapter 7 today, so we'll just be a little bit behind here. But this is chapters 8, 9, and a couple of other chapters. So we'll start chapter 8 tomorrow. All right, any questions? Chapter 7 we're doing today.
Wait, did you say the lab coat was suggested?
Yeah.
Okay. What type of lab coat?
Annie.
Any?
Yeah. I bought cotton's best. If you get 100% cotton, they're this more expensive. Cotton is going to give you a little bit of fire resistance, but it depends on what you can pick up. It's just primarily to protect your clothing,
Oh, okay.
not for any fire resistance. Wow, they're pretty cheap. I mean, something like this is fine. Poly, $11, $10. But if you want cotton, it's going to cost you a little bit more. This is a poly cotton blend. Let's see how much 100% cotton is. $26. So. This is cheap. It depends on how heavy weight the material is. This is probably really lightweight material, but $26 is pretty good. And the reason people prefer cotton is it's more flame retardant. A blue one? Yeah, blue is fine. Any color is fine. White ones tend to get dirty pretty fast. So the cotton one I had to buy. It was mandatory for lab at UCLA. At the time, it was like $70. $70, yeah, it's pretty expensive. 75. Yeah, it can add up. There are going to be ones that are much more expensive. All right, so we're going to look at chemical formula relationships or chemical formula. And so I want to talk about composition here. Mm-hmm.
I actually asked this earlier. What's the difference between composition and structure?
What's the difference between composition and structure? Oh, let's take a look at it. So this is in relation to what? Composition, structure, and properties. So for this chapter, we're just looking primarily at composition, but structure is how things are connected, how things are bonded together. And so, like for example, water. Water has the composition H2O, and then as far as structure goes, water forms H2O molecules like this. And so we just see how things are linked together. Whereas if we look at salt, sodium chloride has a totally different structure. It looks like this. And so water kind of looks like this here. And it occurs in terms of molecules. These discrete units, so they'll have two hydrogens bonded to an oxygen. So these lines, these sticks connecting them are what we call bonds. Whereas something like sodium chloride, there's no discrete molecules here. Instead, what do we call this structure? Water we call molecules. This one we call crystal lattice or an ionic lattice. And so when we have molecular compounds structurally will form molecules. And ionic compounds, how can I tell that this is ionic? And how can I tell this is molecular?
Is made with non-metals?
Yeah. Moleculars are non-metals. Ionic are metal and non-metal. And that's going to form a lattice. In a lattice like this, the sodiums are the small circles here. The chlorines are the large circles. But what stands out is there's no discrete molecule. Like if I wanted a molecule of sodium chloride, I could pick one of these small circles, but which of the big circles belongs to it? And it turns out all of them belong to it. And so it has a different type of structure. It doesn't form discrete molecules, in other words.
But there's not like just one like sodium atom, one chlorine.
No, that would not be called a molecule. If I had just one of these and one of these, we call it a formula unit. So a single unit of this is a formula unit. That's because when we add like here, if I do this like this would be two water molecules like this, right? But when we do a sodium chloride, it's going to be like this.
But it's still a compound, right?
Yeah, it's still a compound. Whereas water would form these discrete units, I'd have two of them. Whereas sodium chloride would just be starting to build up the lattice like this. You know, there are different ways we could build up the lattice. Like this, etc. There are some that are trickier, like this. Ammonium is non-metals. What's the formula for ammonium? Ammonia is NH3. NH4, and what's the charge on ammonium? +1. And do you know nitrate? So ammonium nitrate would be NH4NO3. Would this be molecular or ionic? Now this is tricky because it consists of all nonmetals, but this would be considered an ionic compound. It's considered an ionic compound because it's made up of the ions ammonium and nitrate, which gives us ammonium nitrate. So even though this is all nonmetals, it's considered an ionic compound. Therefore, it's not going to form discrete molecules. So if I had a single ammonium and a single nitrate, we call it a formula unit. And if we add multiple formula units, we build up a lattice. If I have molecules and I have multiple molecules, I just have multiple molecules. So this is the atomic composition. How it's structured is a different story. We can get an idea based on if it's a molecular compound versus an ionic compound, how it's structured. But some things we don't know. And so the atomic composition here is equal to the formula. So carbon. There are multiple structures for carbon. One structure is the diamond structure. Another structure is the graphite structure. Another structure are these C60s, etc. And so there are molecules of C60. There's 60 carbon atoms in a soccer ball type arrangement. And then there are lattices. These aren't called ionic lattices here. These are just what we call covalent lattices. But we have a lattice structure and a molecular structure for carbon. And that leads to different properties. You know, C60 has totally different properties than diamond. Diamond has totally different properties than graphite. And so what we try to do is we try to better understand how composition and structure and properties are interrelated.
So the composition is what it's made of.
Composition's what it's made of, right?
And the structure is how it rearranges itself. The arrangement of the particles.
Yeah, the arrangement, right. That's it. Now composition, we have different ways we can express the composition. We can, water is a pure compound. The typical way we express the composition is in terms of an atom ratio, like H2O. You know, 2 atoms of hydrogen, 1 atom of oxygen. But there are other ways of expressing this. And so this is what we call the atom, or which we'll talk about today. I haven't talked about it yet, but it's the atom or mole ratio. I'll talk about moles in just a minute. Which is equal to an atom percent. This would be hydrogen 67%, oxygen 33%. And so in other words, hydrogen is 67% of water, and oxygen is 33% of water. Or we could break this down in terms of mass. That is, hydrogen is 11% of the mass of water, and oxygen is 89% of the mass of water. And so this is a mass percentage. And so these are 3 ways of expressing the composition of water. We can have this, the formula, the atom percentage or the mass percentage. We can also have the atom ratio. 2 of the 3 atoms, are water. One of the 3 atoms is oxygen. And so we have the atom fraction. We can also have the mass fraction. This would be equal to, well, let me do this. 67 out of 100 hydrogen, or 33 out of 100 oxygen. All right, going over here, this is going to be 11 out of 100 hydrogen, or 89 out of 100 oxygen. Now the difference here is in this would be like, for example, 11 grams out of 100 grams, or 89 grams out of 100 grams here. This would be atoms here. 67 out of 100 atoms are hydrogen, 33 out of 100 atoms are oxygen. And so these are all different ways of expressing the composition. The composition of mixtures, is different. So this would be for a composition of water, which would be a compound. Typically for the composition of a mixture, we use the different ones. So we use for percent, for example, this would be a W over W percent. A W over W percent is just the mass of A component over the total mass times 100%. So if I have salt water, I would take the mass of salt over the mass of the salt water and multiply that by 100%. That would give me the percent salt in water. Sometimes the percent is very small. So if the percent is very small, that is the fraction is very small, I might not use percent. What other options do I have? Let's say this fraction is very small, and even if I multiply it by 100, it's still going to be small. And so rather than multiplying by 100, if the fraction is small, that is, let's say I have very, very, very little salt in there. It's almost pure. I could use instead, what are some common ones I might use? So I could multiply by 100%, or I could take that fraction and multiply by maybe 1,000 or 1,000,000. Let's say I multiply by 1,000,000. What would I call it then? I wouldn't call it a percent. I would call it I'd call it a ppm. So if the fraction were really small, I might go with a ppm instead by multiplying it by 1,000,000. I get ppm. Or maybe that's still too small. I might try to multiply by what's the next one after ppm? ppb. If I multiply by 100, that'll give me my percent. If I multiply by 1,000,000, I'll give my ppm. If I multiply by billion, I'll get my ppb. These are different ways. So, I can express the composition of mixture. It depends on the mixture. I might use percent. I might use ppm. I might use ppb. So let's say I have barely any lead in the mixture. I might just figure out how many parts per billion lead there are in my mixture, because there's very little. For something like water, I don't have very little. I don't have parts per million hydrogen. I have a lot of hydrogen, so percentage works out quite nicely for that. But for mixtures, sometimes we have these mixtures of very little parts. But we have other ways. Do you know what a V over V percentage is? A V over V is the volume of A over the total volume. And we do the same thing. We either multiply by 100 or a billion or a billion, depending on how small this fraction is. It's a V over V. Or we have a hybrid of the two. A hybrid of the two would be a W over V or an M. W stands for weight. We could use M instead. But this is a weight volume percentage. Weight volume percentage, a typical weight volume percentage, we do like grams of A over total volume. So an example of a W over V percent is this 0.9 W over V percent sodium chloride. This is called isotonic saline solution. So if you go to the hospital and they have to give you an IV of saline, it would be 0.9 W over V percent sodium chloride. And what this means is we have 0.9 grams of sodium chloride per 100 what? Milliliters. Yeah. So every 100 milliliters contains almost a gram. Grams of A is what this is. Blank grams of A. This is, or mass of A, mass of A, like I had over here. Grams of A, mass of A, same. You could use any units as long as they're consistent in the fraction, except for this last one. Sometimes we use atom ratios. In mixtures. It's rare, though. This happens for certain alloys. Let's say there's a copper zinc alloy. And what do we know about mixtures? Mixtures we can have, not multiple compounds, multiple compositions. I mean, in other words, what we can have is the composition can vary. So for example, sometimes we might have something like this. 1 copper and let's go with 2 zincs. 1 copper and 2 zincs. So for every atom of copper, there are 2 atoms of zinc in this alloy. But what's to differentiate that from being a compound? What differentiates this from being a compound is this can vary. So for example, this is fine too. Let's say I added a little bit extra zinc. So I had 2.1 zincs for every copper. Is that okay? would this be okay for a compound? The answer is no, this wouldn't be okay for a compound, but for a mixture, this would be okay. This would be okay because for every 21 atoms of zinc, I'd have 10 atoms of copper. Just multiply it. Or let's say I had copper Zn 1.99. And so mixtures have variable composition. And so I could adjust the ratio of the atoms here. And so all this says is if I had 199 atoms of zinc, then I'd have 100 atoms of copper. Just multiply this by 100 and that by 100. And that's okay for alloys because alloys I can adjust the composition. Whereas for compounds, could I do that? It's hard to get it right on. In fact, I might try to get this, but I might end up getting this or this. This one has a little bit of extra zinc. This one doesn't have enough zinc. And so that's the situation with alloys. I could try to represent it, but the situation with alloys is that the ratio is not fixed. Ratio can vary. And it's hard. Whereas for water, can the ratio vary? No. The ratio is fixed for water. And so it's easier not to do an atom ratio because it's really hard to get it to the atom. And so this is why it's not always used. It's really hard to get it to the atom precisely, but sometimes people can get close. And so let's take a look at stainless steel. There are different grades of stainless steel. Stainless steel, there are a whole bunch of alloys of stainless steel. And the grades of stainless steel depend on the composition. So for example, if we look at 304 stainless steel, 304 is one of the most common stainless steels. Let's take a look at the composition. What happened to my composition? Oh, here it is. If you take a look at 304 stainless steel, then it has to have 18 to 20% chromium, 8 to 10.5% nickel. If it falls in this range of composition here, then we can call it 304 stainless steel. But like for example, refrigerators and freezers, the stainless steel on those is not 304. The stainless steel on refrigerators is usually like 430 stainless steel. And 430 will have a different composition, so it's going to have a different elemental makeup. And they'll have different properties. So for example, 430 is magnetic. So you want magnetic stainless steel on refrigerators because you can stick magnets on them, and that makes it useful. Whereas 304 stainless steel is non-magnetic. So if you use 304 stainless steel, a magnet wouldn't stick to this and could be less convenient, less useful. But 304 is much more corrosion resistant than 430. So if you don't want your stainless steel to to corrode, then you'll want a higher grade of stainless steel, like 304. So 304 they use a lot in food and other applications. Let's see. Go to 304. But 304 still can corrode, so there's 316. And 316 is even more corrosion resistant. 316 is what they use in medical equipment. So 304 they might use in kitchen equipment, automotive trim. Automotive trim if you don't want it to rust. 316 they'll use in more corrosive environments or environments that need to be kept cleaner. Like medical equipment, you don't want the stainless steel to start to rust. Pharmaceutical, chemical equipment for manufacturing. Certain kitchen, 316 is much more expensive than 304. So there have been a number of complaints about the Cybertruck. Did you hear about this? Apparently the Cybertruck is rusting.
Oh, yeah, I heard about that.
Yeah. So the Cybertruck definitely is not 304, most likely, and it's definitely not 316. 316 would be medical grade stainless. So apparently, I was thinking the Cybertruck is I wasn't actually thinking it was the 300 series. I was thinking it was 400 series. 400 series is magnetic, but it turns out the Cybertruck is 301. 301 is magnetic, and it's more prone to corrosion. And so this is why the Cybertruck might be rusting so quickly. But apparently it's going to get a higher grade. We'll see. Looks like they may use 304. I don't know. This person has 308 stainless in my pool for the last 15 years. It just has some slight surface rust. Okay. All right, so composition of mixtures, we usually use percent by mass. That's the most common. We rarely use an atomic composition because the atomic composition is going to vary. But for compounds, the atomic composition doesn't vary, and that's fixed. And so this is usually used. And we rarely use percent by mass or percent by atoms because it's a lot less convenient. It's much easier to remember H2O versus H67O33 or H11O89. So percents. All right, so the first thing is determining the numbers of atoms in the composition. So sodium nitrate, which has the formula NaNO3, has the composition what? Well, the composition of sodium nitrate is 1 sodium, it's from this, 1 nitrogen, and 3 oxygens. And so what's the composition of ammonium carbonate? And so ammonium we just did. What was the formula for ammonium again? NH4 plus. And carbonate? CO3. Charge? 2 minus. Good. And so the formula for ammonium carbonate will be we have to make sure the charges cancel. And so it looks like I'm going to need 2 ammoniums to balance out the -2 on carbonate. And so the formula for ammonium carbonate should be 2 ammoniums and 1 carbonate. And so what's the composition? Well, the composition by ions is 2 ammonium ions, 1 carbonate ions. Now let's do the atomic composition. How many nitrogens are there? There are 2 nitrogen atoms. How many hydrogens? There are 8 hydrogen atoms. How many carbons? 1 carbon atom, and how many oxygens? 3 oxygen. So that's the atomic composition of ammonium carbonate. All right, the next thing is, if we know the atomic composition, then what we can get is we can get the molecular mass or the formula mass. The molecular mass is the mass of a molecule the formula mass is equal to the mass of a molecule or formula unit. Not everything forms molecules. So for example, H2O, we can figure out the average mass of an H2O molecule. The average mass of hydrogen, well, hydrogen has 2 isotopes, H1 and H2. H2 is called deuterium. H1 weighs about 1 U, H2 weighs about 2 U. The average mass is 1.01 U. And so we just calculate the average using the equation that we had last time. This is just a 3 sig figs. And so what's more abundant, H1 or H2? H2? How could you tell that H2 is more abundant than H1? And so the average comes out to 101, and it consists of 2 isotopes, H1, about 1 U, and H2, which weighs about 2 U. If they were equally abundant, what would the average be? 1.5. If these were equally abundant, then that is, they occurred in a 1-to-1 ratio, then the average would be 1.5. But they aren't equally abundant. And you're saying that H2 is more abundant because? Or H1 is more abundant? I would say H1 is more abundant because the average is closer to 1. And so the more 1 there is, the more it's going to bias towards that. In fact, could you tell me the abundance of H1 roughly? 99. It's going to be 99% H1. And about 1% H2. That's how I got the 0.01. It's 99% of the way to 1. If I'm 100% of the way to 1, what would it be? It would be 1. And so 1.00 is 100% of the way to 1. 1.01 is 99%. 1.02 is 98%. Does that make sense? If I'm 0% of the way, it would be 2. I'm going to get that range. So that's how I figured it out. But anyway, the average is 101. How much does the average oxygen weigh? The average oxygen weighs 16.00 U. There are three isotopes, 16, 17, and 18, so it's pretty much almost all 16. And so that means the average hydrogen is going to weigh 2 times 1.01 U plus 16.00 U from the oxygen. This is 2 hydrogens here. And that's going to give me 18.02 U, H2O. And we call this the molecular mass. If I go to sodium chloride, the first thing is, does sodium chloride form molecules or does it form an ionic lattice? Sodium chloride, does it form molecules or does it form a lattice? A lattice. It's an ionic compound. And so we can't call this molecular mass. We're going to have to call this formula mass. And so let's get the formula mass. Whereas this one, water, we can call either the molecular mass or the formula mass. It doesn't matter. Both are the same. Whereas over here, the formula mass is not the same as the molecular mass. In fact, there is no molecular mass for sodium chloride. And so what we're going to do is we're going to figure out how much is the average formula unit of sodium chloride weigh. And so we need the average sodium. So we go to the periodic table and take a look. The average atomic masses are given in the periodic table. And we go to sodium, it's 22.99. It's the average. And then we go to chlorine, 35.45. And so the average sodium atom weighs 22.99 U. The average chlorine weighs 35.45 U. And so the formula unit weight would be 58.44 U. Sodium chloride. And we would call this the formula mass.
So you get the mass the same way? You just put a different unit in there?
So the way we could express these are two ways. One, we could just say 18.02 U per H2O molecule. And then this one would be 58.44 U per sodium chloride formula unit. Now formula unit we can just abbreviate F for formula, U for unit. So NaCl formula unit, be the FU. Here. So these would be called molecular and formula masses. Now, we could figure out the percent by mass from this. The percent by mass will be different. So for water, let me do that for you here. For water, the percent by mass is going to equal the mass of component A over the total mass times 100%. And so let's look at the percent hydrogen in water. If we do the percent hydrogen, this is going to be the mass of hydrogen. How much hydrogen is there in water?
2.02.
Yeah, 2.02 U. And how much does the water weigh? 18.02 U. And then we multiply by 100%. So this is going to give me, let's go with 2.02 divided by 18.02 times 100. 11.20. How many sig figs am I allowed? I'm only allowed 3, so I'll subscript the 0. So 11.2% hydrogen. And that means the percent oxygen is equal to what? There are 2 ways of getting the percent oxygen. One is there are only 2 things in here. They have to add up to 100%. So I could just do 100% minus 11.2%, and that's going to give me 88.8% oxygen. The other way I could do it is I could go with how much oxygen, 16.0 U's. It could be grams. I told you the units could be anything as long as the units are consistent. So this could be U or it could be grams. So 16.0 U of oxygen over 18.02 U of water, and that's going to give me the same number times 100%. So that's where I came up with this earlier when I was talking about water. The number here, 11% hydrogen, 89% oxygen. So H11O89 would be representing the composition based on percent by mass. This percent by atom here just comes from this. 2 out of the 3 atoms are hydrogen, so that's going to give us our 67%. And then 1 out of the 3 is oxygen. This is times 100%. It gives us our 33. So 67, 33. What's this? This is CO2. And what we're doing here is we have these red atoms are the oxygens, this black atom's the carbon. And so the average mass of oxygen, 1600, 2 of those, plus the carbon, 1201. This gives you the average mass of CO2. Now, the weird thing is, will we find a CO2 molecule in nature that weighs 44.01? And the answer is no. And the reason for that is because of this. That average is an average of all the isotopes. The most common isotope of oxygen is 16. The most common isotope of carbon is 12. And we'll have another oxygen, 16. And so this is going to weigh about 44, but we have other ones too, heavier ones. So we have 16, carbon 12, and then O17. And then we might have a 16 going to a carbon 12 to an O18. How many of these can we come up with? Well, as many variations as possible. And so we have 3 kinds of oxygen. In other words, 3 isotopes of oxygen and 2 kinds of carbon, 2 isotopes of carbon. Carbon 12 and carbon 13. And so we take all those and then average it, and they average out to 4401. But if I want the individual mass, I have to use the isotopic masses. So if I want the molecular mass for the first one, then I'm going to have to look up. I can't find this in the periodic table. In the periodic table, it gives me the average mass, 16.00. Where can I find the specific mass of an oxygen 16? The specific mass of an oxygen 16 is like 15.994 or something like that. And there I'd have to look those up in the table of isotopes. So I'd get the isotopic masses using the table of isotopes. The table of isotopes. And then I can figure out how much this weighs, and then I can figure out how much this weighs, all of them, and then average those as a weighted average. And that's going to give me this up here. So here's an example. This is ammonium nitrate. Ammonium's NH4 plus. Nitrate is NO3 minus. So this is going to combine in a 1-to-1 ratio to neutralize the charge. And let's figure out how much that weighs. How much does an ammonium nitrate, what should we call it, molecule? How much does an ammonium nitrate molecule weigh? Or should we call it a formula unit? You can't go wrong with formula unit because formula unit is correct for everything. But we can make a mistake for molecules. So an individual unit of this, does it form molecules or does it form an ionic lattice?
It's ammonium.
Hmm? Yeah, it forms an ionic lattice. Even though these are all nonmetals, it's made up of the ions ammonium and nitrate. Since it's made up of ions, it's going to form an ionic lattice. So it doesn't form individual discrete molecules. It's just going to form something that's all packed together. And so structurally, it's different. You know, we'll learn more about the property differences between molecules and ionic lattices, but that's going to come later. For right now, let's just try to recognize it. And so when we do this, this we don't call a molecule. What do we call one unit of this? One ammonium, one nitrate, we call it a, what? No, we don't call it a compound. It is a compound, but I'm just talking about one ammonium and one nitrate. That, what do we call that? We don't call it a molecule. We call it a formula unit. And so how much does one formula unit of ammonium nitrate weigh? Well, one formula unit of ammonium nitrate consists of how many nitrogens? Consists of 2 nitrogens. How many hydrogens? 4 hydrogens. And how many oxygens? 3 oxygens. Now, some of these are very common elements. So let me talk, before we do this, let me talk about some that are common atomic masses. You know, the isotopic masses aren't commonly used. We aren't going to remember any of those. But hydrogen, the average hydrogen weighs 1.01 U. This is to 3 sig figs. However, if we want 4 sig figs, we use 1.008 U. If we want 5 sig figs, we use 1.0079 U. And so we use this in compounds. Use this one. In elements, we use this one. So elements would be like H. If I want 4 sig figs, I'm going to use 1.008 here. And in H2, it's 1.016 U. I use 2.02. I mean, this, sorry, not 1 point. It would be 2.016. This gives 4 sig figs. In compounds, some of the other stuff is heavier, so I already violated this, but it's all right. Carbon is another common one, 12.01 U. So if I have 1 hydrogen, 1 carbon, that adds up to 1302, which gives us 4 sig figs. Nitrogen is also very common. That's 14.01. Oxygen is very common at 16.00 U. So all these are common here. So 2 nitrogens at 1401 gives us 2802. Okay, here I'm not going to use this here. I only use 1008 if I'm dealing with just the element alone, but I have hydrogen in a compound. Hydrogen in a compound, I'm going to use 4 times 1.01 U. This is going to give me 4.04 U. And so if I do that, why do I do that? It's to speed things up. And for oxygen, it's straight at 1600. This is going to be 4800. So when I add mine up, I get 2802 plus 404 gives me 3206. Plus this is going to give me 8006. So I end up with 80.06 U versus they got 80.05 because they had to round it according to the uncertain digit. This is uncertain digit here, this is uncertain digit here. And so having these 2 uncertain digits is going to make the 5 uncertain and the 2 is uncertain. And so we're only allowed 1 uncertain digit, so we drop the 2. And so which answer is more accurate? Their answer is more accurate. My answer is less accurate. But this boils down to accuracy versus speed. In this case, the difference is acceptable. That is, my loss of accuracy here is acceptable because it increases the speed. The calculation's much easier, and then I don't have to do any rounding. And so this is much faster. So this is acceptable. Now, I told you not to do this. I told you not to do intermediate rounding. We don't like to do intermediate rounding, but I just did. I rounded this to 101. But the reason I find it acceptable is because the error is going to be fairly small, and the speed benefit will be great. And so it's worth doing. Now, let's see what time it is. Now I want you to do this. Tell me the percent composition by mass. For ammonium nitrate. We'll do this as your. We'll do this as a little quiz here, and then you can take a break after the quiz, or you can take a break now and then come back and do the quiz. So we'll have a 15-minute break. And just
You're gonna have it for 20. But now we're going up percentage for like self-camping. Is it good? Give the percentages on it.
No, but that's what people did to me.
Huh? Understand?
Oh, I can look like I'm telling you what that. I'm lost. Did you have to get into percentages and stuff like that? Yeah. So like oxygen's 33%.
But then you
Yeah, so yeah.
But
Oh,
once
what?
you find, like, say you do like hydrogen, you still have to find nitrogen and oxygen, right? To get the whole.
Can I see what you're doing?
Sound like.
So
I'm just, yeah, I can.
Oh, right. I told you percent stuff.
so you calculate these, right? And then add them? Oh.
So you have to use the formula, the mass of whatever when you're
So
trying
this
to
is what he
find
was talking
over
about.
the entire volume. Like what we just, like this 80.06 is the whole volume of that.
So again, I know he's fine.
Oh, okay.
Like, what I watch him do is to break mass. To be honest,
Just
it's
find the
like-
percentage.
Honestly, the coffee helped. I got coffee today because I was like, I need to help people. Otherwise, I was working.
No, yeah, it's okay.
He ran out.
Thank you.
Try, so it would
So, sorry. It's just like this, the percentage stuff, right? That's what I was thinking. So it's, I don't know, man. I won't like that. Oh, yeah, of course, yeah. That's exactly what I was thinking.
Right?
Yeah, that's exactly what I was thinking.
Like, that's literally, so
This is what I got. How much is like that? That's not older, it's like max. Okay.
Yeah, but between, yeah, makes sense. That makes sense. Urgency is increasing the amount because you're wait. Yeah, because
No, this is just a people that can understand.
because 80 yeah. Right.
Yes.
Uh-huh.
Should the answer just be 80%?
Yeah.
I don't know. I really don't know. I know, but I'm not big stuff like 80%.
What do you do with the sig figs?
You just follow the sig fig rules.
But I used like 4, then 3, and then 4, but then I got like 100.01%.
Yeah, that's due to rounding error, and so that happens.
Okay.
As long as it's,
Is there another way to annotate this? I feel like, I don't know.
you'd say percent hydrogen, percent whatever,
Okay.
by mass.
Just normal mass or not molecular mass?
No, just by mass.
I got some. No, it's a total mass of all the compound itself. Well, yeah, obviously it's 50%. Yeah, 2 nitrogen, you divide that. Okay, 2 nitrogen, divide 1 nitrogen.
Decimals you can, yeah.
Right there.
Why?
Let's see what's on it. I'll tell you what it is.
Wait, how do you get that? Because you do, you might have done it right. No, it's because I was supposed to run this. No, why not? That's what he said. Because I remember him being $50 not so you don't know.
I did it.
Remember doing some of these?
I did it.
Yeah, exactly.
After you're done with this, you take a break.
I got the same thing as this one, just that if we were to make it into 6 weeks, it would round up. I am. Because the reason why it's from 6 weeks is because you have all this. Yeah, I know. So you might be right. I'm just saying.
No,
is
no,
it honest
I
or
think-
not?
I don't know. Honestly, I don't
I'm gonna just put this as you put it. Basically, got the same.
know.
Yeah, dude.
What's that video?
Cause I'm mad.
Oh, so that I didn't know how it works.
Huh?
So I didn't know. Yeah.
Where do you go? It's on my back.
Oh no.
I'll give you $100 if you go back. I can go to the classroom.
For $100? Yeah.
Hell no.
I'm just writing.
One there, so it was
Oh,
yeah, that's what happens.
no. No, I changed it to 200. 2 ones. But it's an airport, so it's illegal. I think
It's illegal. Oh, look at it. It was not illegal if you have it out in the foul.
sure.
You know? They literally didn't sign up the contract saying they won't do that. Catch my ass.
Oh, no. Well, I mean, it's under your game, so you'll be getting in trouble.
I signed the contract.
Yeah.
It's not. That's it. That's it. Yeah.
Oh no, she can't reach it. Oh no.
Trash. What's it for?
A truck? Genuinely a good truck.
Like stock, like if I was not on like 10.
Well, my thing is like, I'll take like 9 square, but like, I don't like 4 much. I just don't like 4 much. They bring it in. And there's conditions I want to run. Cole's really good, Toyota's just really good.
I really want to see it. But I want a truck. Not like those.
But like, if you see a reliable truck, it depends like,
I just,
you don't want a big truck, right?
nah.
You don't go for a Tucker or a Silverado for a big truck.
What I need a big truck. Huh? It's supposed to, it's kind of like hypothetical.
If you want off-roading, you're gonna.
Yeah, like I'm not gonna go like off-road every Monday after home.
Well, no, I know, but I got people that like, that do off-roading. So it's like, I was interested with the period and stuff. So it's just like,
Just want to look at the machines like that.
I'm like,
Very.
oh yeah.
Good people for this? I don't have, I actually don't have people for this too. Why do you take your resources?
Yeah, the leader. So like super awesome. I know that. I know what's that for. It's not Colorado bit. It's not Colorado bit. Huh?
Right, I show you, as a teacher, I would say, show your work, not students.
Fuck you mean the teacher? No, but like, okay. Alright,
You just divide.
I would just can't do your major. Switch your majors, but not yours.
that's about what I did.
Yeah.
Oh. No, I don't know. Well, cause like, look, I did.
Well, you're close enough.
28.2.
Like, so we got was 34.1. Or that's what
28.2 divided by. That's awesome.
Yeah. Wait.
You said 19. So,
No worries. So bad, oh bad.
Also, the people for that. I said I would close my eyes and say,
You wanna shoot 20 guns?
yeah. But like, Jim
what made you stay with that?
Because you don't get sure.
What are funny you got to it?
I said, I would marry to fast food.
But you know what you should totally get? 620. Like, up about 620. About 620.
But like, what makes you say yes?
One day she'll say yes.
And the cool thing about the 1006 you don't need smart. No, it's because it's any car before 75. Change registration.
Car you, oh, you've been to a lot of black car shows. What's like the coolest car you've seen? If you want to,
It depends. Like, it depends.
like, let's say like,
Because like for me, I'm the McLaren is definitely the big two. When you give me like $6 and like 10 McLaren.
let's say like from the time in the 70s to the 90s.
Oh, yeah, just this weekend. Just yesterday, I went to a car show. There was both stocks with the market.
Really? Whoa, that's really big.
There was a couple of Arbor 40s, some 40 cents. Those are so good.
I know, I was like, that doesn't make sense.
There's a
I keep saying that.
Yeah, I've seen that.
So like it's almost an ugly car.
Yeah.
So these are both. Oh, it's not this car. It's one of the cars that I really like.
like modify some shit. I'm lazy.
This is what I take like.
Yeah.
I don't know if I've seen it fire.
You're into like the
I get done by every. Honestly, over 2 days, this car almost hit me. So like, you know how there's the emergency thing where you go? So this car would now feel like we're trying to merge.
It plays a recording of it revved up. When you rev it up, it plays a recording.
I was in a lot of. I don't. Okay, I was expecting that with my friend playing games. My friend playing games on my phone. You heard? Yeah. I don't remember. Guys, there has to be additional storage because I paid for Apple storage. I paid for Apple storage too. Hey, I paid for Apple storage for my phone. So I have too many phones. I have photos. I know it's
Literally the thing is not in class.
I get it now.
I was like, I'll tell you later.
Yeah.
I was gonna say you're eating ice cream, but okay. Y'all have pretty much. Not even I thought about that. It hit me when y'all were like looking at each other. That's actually insane. I didn't know that. You thought about that. You were like, yeah, what the hell?
Gave her a bit for head.
I didn't watch the movie.
I went to the one in I've been to the one
I forget what. It's not my fault. I might have almost like shit. Did I ever tell you? That shit funny.
Oh yeah, that was it.
I never told you? Front or rear? The front. I know that's what I was like.
Then I saw her.
You've seen it, bro. I was holding on to fucking zip ties.
She's like, that was me.
I know. I saw like her on like hair, and then the punch bag.
How the fuck do I do that? Ah, yes, you see, there is this lovely thing called this, and you just bring it over. Oh, that actually kind of funny. I can't read green. Only a little bit. If it was black, I'm surprised.
Oh, my friend said Mary.
My friend is looking.
Oh my god, that is
You want it?
sad.
I know very little Russian. Well, enough like the word. The cursive looks like shit. You should look at the cursive. It's so bad. They all look like the same. They look like anyone but over and over again. I remember when I started pussing on Russian, you just started like spamming in chat to stop. I remember that was the Instagram.
Yeah, he started Google translating stuff, and I was like, wait.
No, I wasn't. What? I have a freaking keyboard. Yeah.
And I remember because my sister was like,
We were wrecking stuff.
Oh yeah.
Shut up, Peyton.
and this was before.
Oh my god.
But I had just
Y'all on the same floor, the same side. And
we had
I'm
another
You don't know.
no, I'm joking. I'm joking.
You're dumb.
Joking.
No, I am. I know.
I remember I was about to get it, and I just read.
Open.
Like, legit, all you gotta take this.
Yes, I've seen the open hammer before.
They're like,
Yeah. I'm trying to find a store called Open Hammer.
that's so cute.
I've had it for years.
I also want to have it. White. I have the.
Look at it come back.
Little beige.
Not my coworkers.
That one site stopped working at Farm 33.
I know.
I didn't realize that.
I had
I know.
this.
I know it's not working right. It's like the rest. It's just like Asian.
One
I
way
was
is
trying to
just
do my move, like in the corner it says
It's not that I wanted the answers, because I wanted the problem. I didn't want to look on the website, so I had to go to the website.
my shirt. I have this shirt that's a stitch upside down. It says I try. It's like me and every color.
I tried.
You should see me driving.
I'm like totally my friend.
Yeah.
My friend was like, drive my car. And I'm like, you really want me to drive?
But like, they're like,
I'm like, I was supposed to say,
I was telling my friends, every person you did, everything you did is because of your so what you did.
oh, I told my dad.
but I still like it.
My man, you look so tired.
Okay.
The whole time I was playing
I'm an organizer.
Today was my first time in Nessa in like energy. That's big. Yeah. No, I don't count that. Today I was there for like
I think it just automatically converts it.
Yeah. No, three. No.
the first time. The last time I had got my hours was time we didn't go to math class,
High five.
which was a while ago.
I'm scared.
From when-
Like, first off, I can't really check.
Honestly,
Yeah.
high five.
it has to be at a 90-degree angle. It was funny. Oh my god.
That is so good. You can bring up like the just brain meme. You and I are not the same.
I'm trying to sing them.
Take it more.
I will bring this high five
Oh, you
to
didn't go to
someone
school?
else. You will be high fiving me for happiness. Bro, if I had a button. If I had a ring bell. What's it called? It's a ring bell, right?
You don't make that noise.
Yeah.
What?
You don't make that noise.
You're playing my ass.
She said you don't make that noise unless you're playing at your ass.
No,
I know.
What the?
Oh, she said
No.
you don't make that noise when you're
Actually,
pointing
I'm
at
saying
your
like
ass.
this, like I'm hitting a ring bell that's going,
Not the Roblox.
like I'm gonna become hackers on one time.
I'm gonna hit the hunt. Or at least the hunt. It's an Easter event. Hunt. No, the hunt's not on there. The hunt's not on there.
Oh, Nick? Oh, I think so. Really? You kind of-
Oh, the ones with like shading hands? Yeah.
Damn, I worked it forever. We still talking about that. And we all got.
Yeah.
Sometimes it's just like, oh, I was saying cool skins earlier.
So do you need?
My favorite.
You good?
I was just telling you about that at work. And I'm putting a Papa's pizza recipe.
But the only ones that I do want to write
Okay, so what's up there? So my manager was like, this ain't no diet, we don't want you to do.
Let me check my
And then he's like, are you still want food? I was like, I'll take it.
I have the red, the white red.
Look at the top of it.
Oh shit, never mind.
You and my two other team.
I did a year. I put one. I put two.
All right, did you guys get it? The percent composition? Thank you. Was that it? So the question, there was a question about sig figs, but normally when you're given a problem like this, you want to use as many sig figs as possible. So on this particular problem, we could get up to 4 sig figs. So in the percentage, we would want 4 sig figs as well. The only situation is here. If I want 4 sig figs here, I wouldn't use 101. You know what I'd use? Instead of 101? 1008, 1.008. And then if I use that for the mass of hydrogen, I would get 4 sig for that percentage as well. If you didn't, the sig figs aren't that critical on this particular problem, but you could do it. And so there are different ways of expressing the composition. One is the atomic composition using the formula. Another is the percent by mass. And so it looks like, you know, that's going to bias the heavier atoms. So that's going to bias oxygen, oxygen being the heaviest. And so what did people get? People got was about 60% oxygen. Is that it? Yeah, around 60, around 35% nitrogen and about 5% hydrogen by mass. Now by atom, it's going to be different. By atom, you'd look at the total number of atoms. And how many atoms do we have altogether? 9 atoms. 2 nitrogens, 4 hydrogens, and 3 oxygens, so 9 atoms. 2 of the 9 are going to be nitrogen, 4 of the 9 will be hydrogen, and 3 of the 9 will be oxygen. So it'll be mostly hydrogen by atom. So composition by formula is by far the most useful. And so what we want to do is I just want to take a survey and see how those ions are coming along. Let me maybe you can tell me what ion. It could be any ion. Ion, the name in the formula, just to start. So, Ashley, do you have one that pops?
An
Ion, the name in the formula.
hydroxide.
Hydroxide, and what's the formula?
OH the charge of -1.
Yeah, OH -1. That's good. Fran, do you have one? Carbonate. CO3 2-. That's good. Camila, do you have an ion that you can recall? It could be monatomic, anyone. Just tell me the formula and the charge. Well, think about it, and I'll come back to you. Danny, do you have one? Ion that you've memorized recently? Like the last ion that you memorized. Any, not its mass, just the name and the formula. Okay, you can think about it. Email, I'll come back to you. Do you have one that? Okay, what's that one called? Hmm?
I know the letters, but I don't know.
You don't know the name? All right, think of one you can do the name. Emily? Okay. Okay, Leslie, do you have one?
HNO3 nitric acid.
Okay, HNO3, that's good. That's the compound, but I want the an ion. Give me an ion. Any ion. Doesn't matter. We'll come back. Savannah, do you have one?
Hydride ion.
What is it?
Hydride.
Hydride? Oh, what's the formula for hydride?
H negative.
H negative? Okay. It's fine. Hydride. Hydride is one of the ides. No, hydrogen has two common ones. That's why hydrogen, if you look at it in the periodic table here, it's in with like fluoride, those ones. But it's also over here in group 1. So it's positive 1 is a common charge for hydrogen, and negative 1 is a common charge for hydrogen. Caesar is not here. How about Shane? Do you have one?
Acetate.
Okay, what's that? The
C2H3O2.
C2H3O2, the charge?
Negative.
Negative. That's a hard one to remember. And so a lot of people don't get that one. So that's good. You have that one down. Caitlin, do you have one? Phosphate, what's the formula? PO4 minus? Okay. PO4 minus, can somebody else? Minus 1, PO4 minus 1 for phosphate? Maybe I don't know, it's not minus 1. Does somebody have the formula? The charge on phosphate memorized? It's minus 3. Danny, how did you figure that one out?
Phosphorus, the same nitrogen, that column is
Plus 5, yeah. Minus 3, yeah. Except that's for the ides. Like phosphide is minus 3. But the reason phosphate is minus 3 is not because of that. You know, like nitride, minus 3. Phosphide, minus 3. Arsenide, minus 3. But phosphate, we don't do it because nitrate is not minus 3. What is nitrate? Minus 1. So phosphate's different. It's a little different pattern than that. And so there are multiple patterns in there that we have to do. So I don't do it based on that. I do it based on another one in there. There's another way to determine it. So you could come back. We'll talk about it in a second. Let me just go through the survey. Kiana? Oxalate? C2042 minus. That's good. Oxalate's just one of those ones you have to memorize by whatever means you have. Cat? Okay, repeat. HCO3 1 minus. Okay. Bicarbonate, that's good. Grace?
Ammonium, NH4 plus.
Okay, ammonium, NH4 plus. Emil, I think that's the one you're. after Dan?
Carbonate?
Carbonate?
CO3.
Well, Fran already did carbonate, so do a different one.
How about bicarbonate? Is that what I just said?
That one was already done. Kat did that one.
Perchlorate?
Perchlorate, all right.
ClO4 minus?
ClO4 minus.
Or minus ClO4.
Okay, that's fine. Kevin?
Fluoride. F minus.
Fluoride, F minus. That's fine. Tate?
Sulfite, SO3, 2 minus.
Okay, is that with a T or with a D? Sulfite.
Sulfite, with a T.
Okay. SO3 2 minus?
Yeah.
Yeah, that's good. Nick, do you have one?
Sulfite is HSO3 negative? Oh, no, HSO3.
Bisol what?
Bisulfite?
Bisulfite? Yeah. HSO3 charge?
Negative?
Negative. Yeah. Bisulfite's a good one too. Did anything pop in for others? Ari, do you have one? What was the last ion that you memorized? Or any ion that comes to mind. Could be monatomic. Kim, did I ask you also? What ion?
Permanganate?
Permanganate, what is the formula?
MnO4 minus.
MnO4 minus. How about, did any others pop up for you guys? Email, you have one?
Mercury.
Okay.
HG2, 2 plus.
HG2 2 plus. And what do we call it? We call it mercury what? Mercury 1, yeah. That's fine. Danny, you have one? Yeah, ClO3 minus, chlorate. Anybody else? Camila, do you have one you came up with? Ammonium? Ammonium, somebody had already mentioned, but if there's a different one. Emily, Leslie, you guys have any ones that pop up?
Zinc.
Okay, zinc is what charge?
Zn 2 plus.
2 plus, that's correct. Zinc 2 is good. Okay, we'll leave it at that, but you have, all right, today's is the 18th. You have 2 weeks. 2 weeks to learn them all. Not only that, you'll have to do the names of the acids and the names of the compounds in addition to the ions. So make sure you're on pace to have them all memorized by then. Plus, I mean, the exam's not just nomenclature. There's going to be other stuff on the test as well. So you'll have to budget the time to make sure that you can do this stuff. So for example, you'll have a percent composition by mass type problem like this, you know, that sort of stuff. Maybe multiple choice. Let's see. Ammonium nitrate's picked often for percent by mass composition because people want to know how much nitrogen is in ammonium nitrate, because they use ammonium nitrate as fertilizer for its nitrogen content. And its nitrogen content's fairly high at 35% roughly. Oh, I guess I didn't shut down the video here. Recording. It's still recording. Sorry. All right. Now we're going to talk about the mole. The mole. This is a counting unit. Like the dozen. A dozen is a counting unit too. So we could use a dozen for anything. A dozen means how many? 12. And a mole means how many? Yeah, you might have heard this before, but it's 6.022 times 10 to the 23rd. So we use this to count things. So for H2O, we have 2 atoms of hydrogen, 1 atom of oxygen. We could also say this. We could also say that there are 2 dozen hydrogen and how many dozen oxygen? 1 dozen oxygen. So this could be an atom ratio, 2 atoms of hydrogen, 1 atom of oxygen, or it could be a dozen ratio. This is atom ratio. This is a dozen ratio. Or it could be what we call a mole ratio. So we could have 2 moles of hydrogen. We have 2 moles of hydrogen. How many moles of oxygen do we have? 1 mole of oxygen. Mole's abbreviated MOL. It's not much of an abbreviation. We just lose the E. And so a chemical formula is a atom ratio, a dozen ratio, or a mole ratio. They're all the same. And what we need to know is, how's this number defined? Where does this number come from? Do you know where 12 comes from in the dozen? For many, many years, I thought it had to do with something with baking, or donuts, a dozen donuts. But I was wrong. Did somebody know where it comes from? Nor do you need to. You don't need to know where the dozen comes from. But it doesn't come from bakers. I guess it comes from astronomers, the cycles of the moon and the sun. But you need to know where the mole comes from. And you need to know it to 4 sig figs. Actually, here, this is 3, but we're going to add the extra 2. It's not that much more difficult to remember. But why this strange number? Why didn't they choose a simpler number? And the answer is because of the way it's defined. And so you need to know the definition of the mole. 1 mole is defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. Make sure this is still going. So if you have exactly 12 grams of carbon-12 and you counted up all the atoms in there, we come up with 6.022 ... times 10 to the 23rd. There are a lot of atoms in there. And so there are going to be a lot of digits after the decimal point, a lot. And that number is given a special name. This 6.022 times 10 to the 23rd is defined as Avogadro's number, n sub a. That's a lot of number. And then recently, they tried to make life easier. They redefined Avogadro's number. N sub a. So Avogadro's number used to just be 4 sig figs, actually more, but most people memorized it to 4 sig figs. But in this redefinition of Avogadro's number, what they did was they said that Avogadro's number is now going to equal 6.022 times 10 to the 23rd exactly. So they went from 4 sig figs, they just dropped all the other digits, to now this is exact, to infinite sig figs. So why would they do this? Why they did this is to make life easier. So if I had a 1 carbon-12 atom, an atom of carbon-12 is called a nuclide. It's for a specific isotope. How much does that weigh? That weighs 12U. Or 12U per carbon-12. Atom or nuclide. I'll just keep using atom. And so this is called the atomic mass. But not to get it confused, because normally when we think of atomic mass, we think of the average atomic mass. But really this is the atomic mass. And so to not get it confused with the average atomic mass, we call it the isotopic mass. Or isotopic mass. So when somebody says atomic mass, sometimes it's confusing because sometimes they're referring to the mass of an individual atom of a specific isotope, or sometimes they're referring to the average atomic mass. So this is why I usually use average. If I have a mole of carbon-12 atoms, 1 mole of carbon-12 atoms, how much does that weigh? Exactly 12 grams. Or there are 12 grams of carbon-12. Actually, I should write there are 12U of carbon-12. There are 12 grams of carbon-12 in 1 mole, exactly 12 grams. So what should we call this mass? So the first mass is, we're going to call atomic mass or isotopic mass. But I probably shouldn't use atomic mass because that's usually reserved for the mass of the average of all the isotopes, the weighted average of all the isotopes. So this mass, what should I call this one? Yeah, this one is the mass of a mole. If it's a mass of a mole of atoms, then we call it the molar mass. But numerically, they're the same number. And the reason they're the same number is because of the way the mole is defined. and so they're numerically equivalent. And so this is going to bring us to what we were looking at earlier. What was the formula for ammonium nitrate again? Ammonium nitrate. Okay, so we know that nitrogen is 1401. But that 1401 could be either this. It could be 1401 U per average nitrogen atom, or it could be 14.01 grams per mole of nitrogen atoms. And so this could be either an atomic mass or molar mass, depending on what units you want, but numerically they're the same number. Units are different, but the number is the same. And so let's see what people calculated here. So if we're looking at ammonium nitrate, we have two things that we could do. So I don't usually write the units because we could have either. So if I have two nitrogens, it's going to be 2 times 1401, which gives us 2802. And then I have 4 hydrogens. That's going to be 4 times 101, which is going to give us 4.04. And then I have 3 oxygens, which is going to be 3 times 16.00, which is going to give us 48.00. So this is 2 and 4, 6, 0, 12. What do we got there? 80.06, is that correct? And so there are 2 ways I can express this. It's going to be 80.06 U per what? Ammonium nitrate molecule, atom, or formula unit. And so it's going to be a formula unit. So 80.06 U per ammonium nitrate formula unit, or alternatively, I could call it .06 grams per what? Mole of ammonium nitrate formula units, or 80.06 grams per 6.022 times 10 to the 23rd ammonium nitrate formula units.
So it's like the atomic unit and the formula unit, or like the atomic unit and the moles are directly like 1 to 1.
The numbers are the same. The units are different, though. So these two qualify as molar mass. What should we call the first one here? Should I call that the atomic mass? All of these are the total mass, just different units. So these bottom 2 here are molar mass. What's this top one called? Formula mass. Why not molecular mass? because ammonium nitrate does not form molecules, good. And so we call it the formula mass. So, you could put, it doesn't matter, you could put U here or you could put grams here. And so we could say 80.06 grams or we could say 80.06 U, depending on the context we want. And so when we do the percentages, we could either do the percentages in U or we could do the percentages in grams. We'll get the exact same numbers. How many are there in a mole? How many of whatever are in a mole? Well, what we say is how many units are in a mole. And so the number of units in a mole are 6.022 times 10 to the 23rd units in 1 mole. Now with the new definition of the mole, this is exact. The old definition, this would be 4 sig figs. They just made it exact so it's easier to remember. So if I have 1 mole, how many units are there? Okay, if I have 2 moles, how many units are there?
6.0.
Yeah, 2 times that, 12.044. If I had half a mole, how many units are there?
1/2 parentheses.
1/2, or 3.011. If I have a quarter mole, how many units are there? Well, it would be a quarter of it. And so I have a quarter mole. A sample consists of a quarter mole of ammonia. How many ammonia molecules? Well, ammonia, what's the formula for ammonia? NH3. This is ammonia, which is neutral. And NH4 plus is called ammonium. And so it's not NH4 plus for this one, it's just NH3. Ammonia is a molecular compound, and we have a quarter mole. And so we could use dimensional analysis. 0.25 moles of ammonia. And we know that there's 6.022 times 10 to the 23rd ammonia molecules. In a mole of ammonia molecules. And so the moles of ammonia cancel, and so it's 1/4 this. It comes out to 1.505 times 10 to the 23rd ammonia molecules. How many sig figs am I allowed here? Well, how many sig figs is a quarter mole? 2. 2 sig figs, or maybe it's exact. So this could be a hypothetical question. In a quarter mole, how many? So if I just ask you, how many molecules are in a half? Well, how many sig figs are in a half? 1/2. Is that 1 sig fig? I said half a mole. 2? Or I just asked you, how many units are in 2 moles? And you said it would be 2 times this. Well, how many sig figs is that? Well, if I asked you, how many molecules are in 2, what do you think? Am I just estimating anywhere from 1.5 to 2.4? Can't decide, or do I mean exactly 2? And so in certain questions, it means exact. And so if I asked you how many how many molecules are in 2 moles, I might be talking exactly 2 moles. If I'm talking exactly 2 moles, how many sig figs is that? Infinite. And so they're asking how many are in a quarter mole. This could be infinite sig figs. That's possible. And so it's either 2 sig figs or infinite that is exact. It depends on the context of the question. And so if I asked you how many molecules are in a quarter mole, you just take a quarter as exact and then estimate how many. Estimate how many comes from this. And if this is 4 sig figs, then we should have 4 sig figs in our answer. But we now know that this is not 4 sig figs anymore. This is infinite. And so we're allowed infinite. But when we look at what they did here, let's say this were 2 sig figs and this is 3 sig figs, then we should have 2 sig figs in our final answer. But they have 4. And so even though this has been rounded to 3 sig figs, we should round this down to 3, if we treat this as exact.
So is it actually 1.51, or is this the exact?
I would, let's say we do a quarter as exact and then treat it as 3 sig figs, then you're right. This should have been rounded. And I'd like to see this on tests. On tests, I don't like the final answer. I want to see how you rounded it. And so this would have been rounded to 1.51 times 10 to the 23rd. If we treat this as exact, then this is 3 sig figs.
So we use 1.575 because you use 4 sig figs?
Yeah. No, I just copied their answer here, but it would be correct. I don't know. Let me take a look at it. And so you take Avogadro's 6.022. 6.022 divided by 4. And actually it's 1.5055. It's 1.5055000, an infinite number of 0 times 10 to the 23rd molecules. And that is, if I treat this as exact and this is exact, then I'm allowed as many digits as I want. So we talked about the molar mass already. Calculate the mass of calcium fluoride. So normally when we have the mass, they don't specify. Is that now calcium fluoride? Let's get the formula. Calcium is what? Ca charge. 2 plus. Fluoride is F charge minus 1. So this is calcium fluoride. How many fluorides are we going to need for each calcium? 2. And that should balance it. And so calcium fluoride is CaF2. Now the mass, what are they talking? Is this molecular or ionic? Calcium fluoride, does it form molecules or lattice? No. Not molecules. Why? It's ionic. It consists of the ions here, and it's metal and a non-metal. Metal and non-metal is going to be ionic. And therefore, we wouldn't call it molecular. We're going to call it the formula mass or the molar mass. They're not specifying. They just want the mass. So the formula mass is going to be U per formula unit. The molar mass is going to be grams per mole of formula units. And so 2 different units there. In the periodic table, they don't tell us if it's the atomic mass or the molar mass. If we go to calcium, let's take a look at what calcium is on my periodic table here. Divisions. You see it's 40.08, but there are 2 units I can associate. What are the 2 units that I can associate with this 40.08? This is 40.08 U per, so this is 40.08 U per calcium atom, the average calcium atom. So you take all the isotopes, you get the weighted average, and you come up with 40.08 U per average calcium atom. So it would be U per atom. And we call that what? 40.08 U per atom, we call that the atomic mass. And the atomic mass refers, in this case, it refers to the average of all the isotopes weighted by their natural abundance. Because of the way the mole was defined, we have another unit that we could use for this. What would the other unit be? It would be 40.08 grams per mole of atoms. And so when they ask us to calculate the mass, they're doing the molar mass here. It didn't say calculate the molar mass, it just said calculate the mass. So we don't know. And so we usually what we do is we leave the units off. And so this is going to be 40.8. And the fluorine's an easy one to remember, although it's not as common. Fluorine to 2 decimal places is 19.00. So we have 2 fluorines at 19.00. That's going to give us 38, so this is going to give us 78.08. Now we have 2 units that we could use for this. It's going to be 78.08 U per what? Not per atom, but per calcium fluoride, not molecule, but calcium fluoride formula unit. Or it could be 78.08 grams per mole of calcium fluoride formula units. So when it asks us to calculate the mass, we don't know which units they're after. And so we could do the molar mass. They did the molar mass, but they didn't ask for the molar mass. They just asked for the mass. And so we could get the molar mass over here, or we could get, what do we call this? The formula mass. Do we work with formula units, individual formula units? No, they're too small. And so normally we work with moles of formula units. So how much is that? If we look at iron, the average iron weighs 55.85 U. If I have a mole of iron atoms, then it weighs 55.85 grams. Well, 55.85 grams is a lot, but not too much. And so a mole of iron is just about the right amount for a lot of reactions. This would be a mole of aluminum, a mole of mercury, a mole of sodium, a mole of copper. And back here we have a mole of nitrogen. That looks a little small. It should be a little bit bigger. This is a mole of copper 2 sulfate pentahydrate, a mole of mercury 2 oxide, a mole of water. A mole of water is 18 milliliters, or about 18 grams. A mole of oxalic acid, a mole of oxalic acid dihydrate. And so that's brings things into perspective. So at a microscopic level, we work with mole quantities, versus formula unit quantities, that is individual atoms and molecules and formula units. You're carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. Now, this is going to be how many sig figs over here? 3 sig figs. Barium chloride. What's the barium ion charge? and chloride. And so we'll need 2 of those, so we're going to get BaCl2. And chloride. So barium, I'd like to go 2 decimal places for everything, and that's going to be 137.33. And then chlorine I like to memorize here because chlorine's fairly common. Chlorine is 35.45. And so this is going to give me 70.90. And so we get 3, 12, 14, 15, 140. Or no, not 140, 270, 208, 23. I don't like to do what they did here because I just like to keep things consistent, 2 decimal places. So what they did here was they used barium with only 1 decimal place. That requires additional rounding. And so I don't normally do that. I just go with 2 decimal places. This would be BaCl2. How many grams? So if we have 0.0360 moles of BaCl2, then we know this number. This number is going to have the units U per formula unit or grams per mole of formula unit. So we're just going to use this. 208.23 grams per mole. This is going to be grams of barium chloride per mole of barium chloride. Formula units. I'll just leave off formula units there. And so I'll get 0.036 times 208.23. I end up with 7.49. How many sig figs am I allowed? I have 3 sig figs here. And how many sig figs do I have here in the molar mass? 5 sig figs. So I'm going to have 3 sig figs. So I'm going to carry 1 extra. 7.496, which I'll round to 7.50 grams of barium chloride. Is 0.036 moles. Having some technical difficulty here. Okay, I think so we're going to do a little bit of stoichiometry. Have you heard this word stoichiometry? Stoichiometry refers to quantity relationships. Let's see if I can find a piece of pens now. And so we've been doing stoichiometry a half moles, 2 moles is double that. Those are all quantity relationships. The stoichiometry we're going to do, let's see. We're typically interested in mole quantities. So moles will be at the center of our stoichiometry. This is called the stoichiometry map. And from moles, we can go to different places. Let's see. Okay, this is back. Let me just save this. And so I'll put moles in the center here. We can go from grams to moles or moles to grams. And what we use for the relationship between grams and moles is we use the molar mass as a conversion factor. We either flip it one way or the other. And so molar mass, to go from moles to grams, we use the molar mass as is grams per mole, or we use the inverse of it, moles per gram, either way. And then we could go to the number of units. For the number of units, what we use here is we use Avogadro's number. Avogadro's number is going to be the number per mole, or we flip it over, mole per number. Invert it. And so these are typical stoichiometry calculations that we do in the stoichiometry map. In terms of macroscopic quantity versus particulate, macroscopic we use grams as a unit. At the particulate level, we use U. At the macroscopic quantities, we have moles. At the particulate level, we have formula units or molecules. And so this is going to be in macroscopic quantities when we're dealing with moles here. But it could also be particulate as well. Here, quantity of particles, this will be particulate. Mass in grams, that's macroscopic. Yeah. And so let's take a look at an example calculation here. Sure, I have enough time to finish. Determine the mass in grams of 3.2 times 10 to the 24 molecules of sulfur tetrafluoride. What's the formula for sulfur? S. So sulfur tetrafluoride would be SF4. This is what we call a binary molecular compound. And so it's going to be molecules. And what we're going to do is we're just going to go here. We have 3.2 times 10 to the 24 SF4 molecules. And then we're going to convert that from molecules to moles in this case. And that is 1 mole of SF4 contains 6.022 times 10 to the 23rd SF4 molecules. Okay. Once we have moles, then we're going to figure out how many grams by looking at the molar mass. The molar mass of sulfur is 32.06, and then we have 4 fluorines times 4 times 19.00. And this is going to give us a molar mass of 10806. So we'll just put it in here, 10806 gram. This is either U per molecule 108.06 U per molecule, or 108.06 grams per mole of molecules. And so we have a mole of molecules here, so this is going to be 108.06 grams per mole. This is grams of SF4 per mole of SF4 molecules. And that should give us this. What I don't like about how they did it is they didn't show me how they rounded it. So what I'd like you to do is I'd like you to show me what digit got dropped. And so on a test, you would do 3.2 times 10 to the 24 divided by 6.022 times 10 to the 23rd times 108.06. And that gives 574.2 grams of the SF4. Now this has 2 sig figs. This has infinite sig figs, and this is 5 sig figs. So our final answer, we have to round to 2. So this is going to just be 570 grams SF4. Or, to, in scientific notation, 5.7 times 10 squared grams. And so this is a calculation where we started off with the number of particles, and then we converted that to moles, and then from moles we converted that to grams. Stoichiometry math. So we did a percentage by mass already, and so the percent of A is all just the parts of A, grams of A over grams total, or it could be pounds, whatever units you use is to be consistent. And so here's the percentage by mass of calcium fluoride. You use U, but you could also use grams. It doesn't matter. And so we want the grams of fluorine over the grams of calcium fluoride. So we have 2 fluorines, double that, and then the mass of calcium fluoride, 78.08 grams per mole. So times 100. This gives us 48.67% fluorine. Calculate the percentage composition by mass of aluminum sulfate. And so we have aluminum is 3+, sulfate is SO4 2-. So there's a quick way of doing the formula here, and that is to cross multiply. So the 3 goes down here, and then the 2 would go down here. And so what we end up with is Al2SO4 3. So it's like cross multiplying, and that's what we end up here, Al2SO4. So we have 2 aluminums at 2698, 3 sulfurs at 3206, and 12 oxygens at 16. That gives us a total mass of 342.14. And then we could figure out the percent aluminum. 2 aluminums over the total times 100, 15.77% aluminum. And then the sulfur, 3 sulfurs at 3206 over the total times 100. And then the oxygen. Now, may or may not add up to 100%. They said check it to make sure it adds up to 100%, but you could be off a little bit. It could be off a little bit due to rounding, so don't worry about it too much if it's off, like 0.1 plus or minus. It's usually due to rounding error. Aluminum chloride is 38.35% chloride. What is aluminum? Aluminum is Al3+. What is chlorate? ClO3 charge? This is not chloride. Chloride is what? Minus, Cl minus. The charge on chlorine is -1. What is the charge on chlorine and chlorate? Well, oxygen is what normally? It's oxide -2. That means chlorine would be, if oxygen's -2, and we have 3 of them, and then we have 1 chlorine at +X, this has to add up to -1. So what is +X? Yeah, +5. So chlorine's +5. There's a world of difference. between chlorine in the +5 and chlorine in the -1. So if chlorine's in the -1, it's very stable. Like chloride, I've eaten chloride, and you've probably eaten chloride all the time, you know. The sodium chloride contains chloride. Are you worried about any risks? No, except maybe high sodium. But would you, if you ran out of sodium chloride, would you sprinkle sodium chlorate on your French fries? No. Eat those, or whatever you're eating. And so this is not chloride, this is chlorine. Chlorate contains chlorine in the apparent +5 state. So this would be chlorine. Well, anyway, 38.35, let's convert it into fractional form. So this would be 38.35 grams of chlorine per 100 grams of aluminum chlorate. What's the formula for aluminum chlorate? It would be AlClO3,3. Need 3 chlorates to balance. That's what they have here. But what they do is they do this milligram stuff, and they write this as milligrams. I do extra steps in doing this. I don't like to do too many different variations of this, but that's okay. I probably would have done it like this. I probably would have done 50.0 milligrams of aluminum chlorate convert that to grams. And then convert that to moles. Actually, I don't have to convert it to moles. Normally I'd convert it to moles, but we don't, in this case, have to do that. The reason we don't have to do that is because we have something that gets rid of grams of aluminum chlorate. And what gets rid of that is this. So we could say that there are 38.35 grams of chlorine per 100 grams of aluminum chlorate. And so this saves us some step here. And then reconvert it back into milligrams, 1,000 milligrams per gram. So the 1,000 cancel, and that leaves us with this. This will tell me how many grams of chlorine there are in this. The percent composition by mass, we did that empirical formula. There's one calculation I forgot to do. Let me go back and take a look at this one here. There's another way we could have done this particular calculation here. Or this. We could have started off with 3.2 times 10 to the 24 SF4 molecules. And we have the mass here. I know how much an SF4 molecule weighs. It weighs 108.06 U per molecule. So sorry, let me add this here. 108.06 U per molecule of SF4. And so the molecules cancel, that leaves me with U. And the last thing I need to do is I need a relationship that relates grams and U. And so let me insert that here. the gram to U relationship. And the way we're going to get that is by the definition of the U and definition of the mole. So we combine this. The definition of the U, what was it again? It was 12 U per carbon 12 atom or nuclide. And what was the definition of the mole?
12 grams.
12 grams per
12 grams
per mole. So 1 mole is equivalent to 1 mole of carbon 12 atoms is equivalent to 12 grams exactly. And then Avogadro's number, what was that again? 6.022 times 10 to the 23rd atoms per mole. So when we look at this, carbon 12 atoms cancel out carbon 12 atoms. Moles of carbon 12 cancel out moles of carbon 12. 12 cancels out 12. And so what are you left with? What you're left with is this. There are 6.022 times 10 to the 23rd units in 1 mole. Or actually, not. Let me reiterate that. There are 6.022 U's, atomic mass units, per gram per G. And so this tells us U per G, U per gram. In other words, there's an Avogadro's number's worth of atomic mass units in a gram. And so we can go back here and finish this particular problem. We know how many U that is. And what we can say is that there are in 1 gram 6.022 times 10 to the 23rd U. And this will lead to the same number here, 570. So 2 different ways of doing this. All right, I need to finish this up in the time remaining. All right, we have something called the empirical formula and the molecular formula. The empirical formula is the simplest ratio. The molecular formula is the formula for the molecule. And so the molecule consists of 4 carbons, 10 hydrogens, but when we look at the simplest ratio, it's a 2 to 5 ratio. So this is like half the molecule, but we aren't going to have half the molecule exist. We want the molecular formula. And so sometimes we'll lose some information regarding this. Why do we care about the empirical formula? Let's say you have some kind of mixture and you separate it into the components. The components would be compounds or elements or elements that make up the mixture. And when we take a look at the compound, we want to know what is the composition of the compound itself. And so there are different ways of determining the composition of the compound. One way of determining the composition of the compound is something called elemental or chemical analysis. Another way of determining the composition of the compound is by measuring its properties and comparing it. But if we have this unknown, say unknown compound here, and we want to figure out what is it, what we'll do is we'll send that for elemental or chemical analysis, and from that we'll get the mass of the elements present. And if we know the total mass, we can take these two things to get the percent by mass composition. And so from analysis, we usually end up with this, or this. You take it one step further to do the calculation. From these two things, we can determine the empirical formula. If we want the molecular formula, we have to do one extra step. And so we have to have further analysis. In other words, what we need is we need the molecular mass or molar mass. And then we can get the molecular formula. So let's say from chemical analysis, we send out a sample. And this gives us the masses. And then from the masses, we want the moles. And from the moles, we'll get the simplest mole ratio. The simplest mole ratio is equal to the empirical formula. So let's say we got an empirical formula CH. In order to get the molecular formula, we need to know how much the molecule weighs. So let's say the molecule weighs 26 U. If the molecule weighs 26 U, could it be CH? How much would a CH unit weigh? Carbon is 12, hydrogen's 1, this would weigh 13. But if the actual molecule weighs 26, then we know that the molecule is twice as big as the empirical unit. And so we have different choices. So in this case, this would be the empirical unit. And the choices we would have is this. One is that the molecular mass is 13. If the molecular mass is 13 U, then it matches. Or it's 26 U. Or it's 39 U. And so we need that. And let's say further analysis says it's 26 U, and therefore the molecular formula would be C2H2. Like that. If it came out to 13 U, then it tells us the molecule must be CH. If it came out to 39 U, it would be triple that, C3H3. So we're going to take a look at this. A sample of a pure compound. So after separation, we're left with the components, and the components are going to be pure. So we have this compound. So we send out this compound for chemical analysis. And what comes back is this. We got 1.61 grams of phosphorus and 2.98 grams of fluorine present. And so 1.61 grams of phosphorus, 2.98 grams of fluorine. So what we can do is we can get a percent composition by mass. You know, this many grams over the total, this many grams over the total. But for compounds, we don't like to use percent by mass. For mixtures, it's fine. For compounds, we like to use the atom ratio of the formula. And so right now we have the mass ratio. So the first step is we want to get the mole ratio. And so we're going to convert this to moles of phosphorus. And then this we're going to convert to moles of fluorine. And then what we want to do is we want to end up getting the simplest mole ratio, whole number mole ratio. Once we get the simplest mole ratio, that's what we call the empirical formula. Now, if we want the molecular formula, we need one more thing. We need to know how much the molecule weighs. And so we need to know the molecular or molar mass. What if it doesn't form molecules? If it doesn't form molecules, we stop here. So for ionic compounds are always the empirical formula. But for molecular compounds, we'd like to go one step further. And so for molecular compounds, we want the molecular formula, not the empirical formula. In this case, this is phosphorus and fluorine. Phosphorus and fluorine is going to form an ionic compound or molecular compound. It's going to form a molecular compound, so we'd like to take this all the way. Let's see if we can do that. So we had how many grams of phosphorus? 161 and 298. So the first step is we're going to do a gram to mole conversion. So we need the molar mass of phosphorus. We can get that from the periodic table, 30.97 per mole of phosphorus. And so how many moles does that come out to? So we got 161 divided by 30.97. Oops, let's try it one more time. 161 divided by 30. .19. How many sig figs am I allowed? 3. And so I'm going to carry 1. 5.198 moles of phosphorus. And then fluorine, a mole of fluorine is 19.00. This is a lot easier number to memorize. Grams. So we'll do 2.98 divided by 19. .1568 moles of fluorine. Actually, I think I screwed up the previous calculation. 161 divided by 30.97. Yeah, I did. 0.05198 moles of phosphorus. So we get the mole ratio. The mole ratio is going to be P 0.05198, F 0.1568. All right, can you name this? You aren't going to be able to name this because this isn't in the proper form. What we have to do is we have to get in the simplest mole ratio. What happened to my black pen? It ran out. And so to get it in the simplest mole ratio, what we're going to do is we're going to divide it by the smallest to kind of normalize it. And so this is going to give us P 0.05198 divided by 0.05198, F 0.1568, divided by 0.05198. And so what does that come out to? So I'm going to take 0.1568 divided by that. It comes out to 3.016. Okay, then we're going to do a couple of things. We're going to round or multiply. So in this case, if it came out to x 0.5, we'd multiply by times 2. If it came out to x 0.3, we'd multiply 3 times 3. Depends on what x comes out to here. In this case, it doesn't, and so what we're going to do is we're just going to round. We're going to round this to PF3. PF3 is the simplest ratio. This is the empirical. Now, to get the molecular formula, we need to know how much the molecule weighs. It might weigh this. What does this weigh? And so it could be PF3, or it could be P2F6, or it could be P3F9. These are going to weigh different amounts. And so what we need is we need one additional piece of experimental data, which is going to tell us which one it matches with. If the molecule weighs the same as PF3, then that's it. It could weigh double, or it could weigh triple, etc. Since we don't have that information, we have to stop here, even though this forms molecules. If this were ionic, then we're fine.
I'm confused with the random multiply.
I'm sorry?
I'm confused with the random multiply thing. Like, so if it was like 1.5, it would multiply the 1 times.
Yeah. Let's say if it were something like this. Let's say we came out to PF 1.5. Should I round 1.5 to 2? In other words, should I go PF2, or should I double the whole thing and call it P2F3? I'd probably double the whole thing and call it P2F3 rather than round it. Does that make sense? What if it came out to PF 1.3? Should I round it down and just call it PF? Or should I triple the whole thing? If I triple the whole thing, then I'd call it probably P3F9. Or no, if I triple that, what would it come out to? 1.3, 2, 3, 4. P3F4. It depends on if you feel comfortable rounding that down or rounding this up. It's quite a big round. Do you see that? And so what might be better is just to multiply it instead of rounding. But for ours, it's fine. We could round this down. It's so close. We didn't really have to worry about it. So we need additional piece of data, and we need to know how much the molecule weighs. How do you weigh molecules? We need the molecular mass. So one way of doing this is to shoot the molecules into an instrument called a blank spectrometer. What was the name of that? It is the mass spectrometer. So if we take some molecules, then we can introduce these into the mass spectrometer and weigh the molecules individually and figure out how much they weigh. If the molecules weigh the same as PF3, then we're set. It's PF3. In fact, when we weigh the molecules for this, it comes out the same. And so 3 times 19 is 31. It came out to 88. And from the mass spectrometer, it was 88U. Well, this thing weighs 88U. And since it's a match, 88U in the mass spectrometer, this weighs 88U, then the molecular formula and the empirical formula are the same. Let me just do one. Oh, actually, we're out of time, so I'll stop here. If you didn't collect your homework from the exam, I didn't think I passed these back. I have your homeworks here if you'd like to grab it. Now, or you could grab it tomorrow. All right, thanks. It's just in the pile there.
Let's get our exam.